Okay, so I'm getting to the part in the series of space-time algebra lectures where we really dig in to the quad vector or pseudoscalar in the Clifford algebra and working with it just as we work with complex numbers in complex analysis. So that's exciting because that's the line of reasoning that I've been following in these videos, and we'll see what new insights I get when I actually dive in and study this stuff. Today, the question that came up in my mind, well, this being a spiritual channel, the advice came from my spirit guides, and it was to examine and think more about the covariant derivative. And, the covariant derivative is very useful in constructing tensors for general relativity. In fact, the covariant derivative itself is constructed from various instances of the flat space metric. And so a covariant derivative operator is made up of a more ordinary partial derivative operator put together with a Christoffel symbol, which is the thing that's made up of the various instances of the flat spacetime metric, or not so flat spacetime metrics. And so when you put those two together, what you have is a way to differentiate something across all reference frames, because the Christoffel symbol will connect your derivation to whichever frame of reference you'd like, to whichever basis you would like. And then the covariant derivative operators are multiplied and summed to create a huge curvature tensor, the Riemann tensor. And from that, we can derive the Ricci tensor, which is what's used in the Einstein gravitational field equation, as well as the Ricci scalar. Also, the conformal tensor, the Weil tensor, which we can use to quantify and characterize gravitational waves. So, far out and amazing things. And of course, these curvature-based concepts will find their way into the space-time algebra, or at least the version of it that I'm attempting to create. How? Not entirely sure yet. I mean, covariant differentiation is part of quantum field theory, with the using the gauge symmetries that govern the various different quantum fields, such as the electron field, for instance. ultimately, there just seem to be too many of what would seem to be fundamental fields in particle physics and in quantum field theory. Does there really need to be a separate field for the top quark versus the up quark? I mean, how many quark fields are there? It seems too many. You know, I could see that there might be separate fields for electrons, positrons, fermions versus bosons. But I suspect there are more unified versions of these quantum fields. And I wonder if that is something that the space-time algebra could shed some light on. All right, well, just some thoughts, just kind of making a record of where my thoughts are proceeding as I work on my own theory.